Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this course on finite fields. This course has 4 broad modules. As you can see, here is a lecture wise topics list of topics, and these are divided into 4 broad categories. First 2 lectures on fundamentals, which contains materials on sets, mappings and integers. Then we have 2 modules on algebra, modern algebra. First is on groups, there are 4 lectures, and the second is on rings and polynomials, which has 6 lectures, and the lastly we will have 8 lectures on fields and finite fields. So, some of you may already know some of the background material before that I covered here before coming to fields and finite fields. This course is intended to be self-sufficient in nature, so that all the background material required to understand this course is also covered as part of the course, and that is why there are these 3 modules before coming to fields and finite fields. However, one topic in rings and modules you can see is highlighted, simple constructions of fields. This can be considered as part of the last module as well. Other than that, if you know some of the topics already, it is okay to skip those corresponding lectures and go to the subsequent lectures. Now, I will show you the detailed content, lecture wise content for each lecture, so that you know which lectures you already know and which ones you do not. Now, before going there, for most of the course, this book by Liddell and Narrator, Finite Fields, will be the reference book. Most of the material is available in that book. Here is the detailed lecture wise content in the course. First 2, as I said, are on sets and integers. Next 4 are on groups. Then next 6 are on rings and polynomials up to 12, and then from lecture 13 onward we come to fields and finite fields, and we end with lecture 20, which is on linearized polynomials. Okay. So, I hope you have a good time in the course. We will now start the first lecture. In this class, we will cover some basic mathematical background related to set theory. So, to start with, what is a set? A set is basically a collection of well defined objects. It is a collection of objects, and the phrase well defined is important, because when we try to define a set, there should not be any ambiguity about which objects are in that collection and which objects are not in that collection. Now, for example, the set of all people can be a set, can be defined as a set. Set of all players in a match can be defined as a set. The set of numbers 1, 2, 3 and 4 can be called a set. The collection of all real numbers in the range 1 to 2 can be called a set. A set can have either finite number of elements or infinite number of elements, and depending on that the set will be called a finite set or an infinite set. So, coming back to the phrase well defined, as I was saying, sometimes some definitions can be ambiguous, and one example is a famous paradox called Russell's paradox. So, suppose someone defines a set as the set of all sets which do not contain themselves. So, the objects in this set are sets themselves, but not all sets, only those sets which do not contain themselves, right. Now, this definition is confusing and for valid reasons, and that this is actually not well defined, as we will see. So, for example, if we take the set S itself, it is a set. So, there is a question of whether S itself is an element of the set S, right. Suppose we start by assuming that S does belong to S, then by the definition of S, it should not be in S, because the set S only contains those sets which do not contain themselves, whereas S contains itself. So, S should not belong to S. So, this is a contradiction. But on the other hand, if we start by assuming that S does not belong to S, then again S should be in S, because S contains all such sets which do not contain themselves. So, this means that S belongs to S. So, this also leads to a contradiction. So, it is not, one cannot determine from the definition of the set S whether S belongs to itself or not. So, its elements are not well defined. So, there are various flavors of this paradox in different forms, and another form is the following, where it is said that in a village there is a barber and he shaves all men who do not shave themselves. Now, one can define the set S to be the set of all men who the barber shaves, okay. In other words, who do not shave themselves. But given the statement that the barber shaves all men who do not shave themselves, this set is not well defined, because now there is similar difficulty as before whether the barber himself belongs to that set or not, because if barber shaves himself, then according to this definition barber should not shave him, and if he does shave does not shave himself, then he should shave himself, right, because barber shaves all men who do not shave themselves. So, again there is it is not clear whether the barber belongs to the set of men who the barber shaves. So, such definitions we will say that these are not well defined sets. If the elements, we cannot determine whether some which elements are there and which elements are not there. Okay. Now we will see some operations on sets. First of all, if there is a set A, I mean in any context usually there is an universal set, which means the set of all elements which are of which are relevant in that context. So, that is the universal set, and then all other sets defined in the context will be subsets of that universal set. And given a set A, its complement is defined as the set of all elements which are not in A, that is the universal set, it is there in the universal set, but not in A. So, X is in the complement if and only if X is not in A. Given two sets A and B, their union is defined as the set of all elements which are either in A or in B. Right. So, if you have sets like this A and B, two sets, their union is defined is this shaded area that is shown here. Now, this union is defined for a pair of sets, but you can extend this definition to any finite number of sets clearly, because you can take, if you have sets A1, A2, etc. An, then you can first take A1 union A2, then take union of that with A3 and so on, union of An and so on. So, but one can also extend this definition to any collection, including an infinite collection of sets. So, suppose we have an infinite collection of sets AI, where I belongs to an arbitrary indexing set A I. So, this can be infinite set, finite set, or even an uncountably infinite set. So, there can be many sets, and their union is also defined in the same way, that an element is in the union if and only if it belongs to at least one of those sets AI for some I. Now, intersection is defined as the set of all elements which are there in every set, that is in both A and B, and just like union, you can extend the definition to any finite collection by taking pairwise intersection at a time, but the intersection is also defined for any collection of sets in the same way, that an element is in the intersection of this collection if and only if it is there in each of them. So, we will then write intersection I belongs to I AI. Similarly, union can also be written. For example, if we take the set A to be the set of even integers, that is integers which are divisible by 2, and B to be the set of integers divisible by 3, then what is the A intersection B? It is the set of integers which are divisible by both 2 and 3, which means they are divisible by 6. Similarly, A union B will be the set of integers which are either divisible by 2 or divisible by 3. So, as I was saying, for any infinite collection also one can define union and intersection, and here is one example. AI can be the set of all integers above I, greater than equal to I, and their union then we will have so set of all natural numbers which are greater than equal to I, then the union of AIs is the set of all natural numbers. And what is the intersection of these sets? The intersection of these sets is so intersection of these sets is empty set, because no element is there in all these sets, because if you take any integer, for example 7, it is not there in A8, it is not there in A8. So, every integer, every natural number is not there in some of these sets. Now, if all the elements of A belongs to the elements of B, then we say that A is a subset of B and write it this way. Now, of course, this means that subset are equal to, even if they are the same set, then we say A is a subset of B, but if it is not equal, but it is a subset, then we say that it is a proper subset of B. We sometimes write it just this to mean that it is a proper subset of B. In some books it is written as A subset not equal to B, which means it is the proper subset of B. Now, there is a very important result called De Morgan's law about union, intersection and complement. Let us see that. So, if we take two sets A and B, if you take their union and then their complement, it is same as A complement intersection B complement. So, this can be seen very easily using this type of Venn diagram. These are called Venn diagram. Okay. So, what is A union B complement? So, this is the universal set A union B is this whole thing, and its complement is this outside, right. Now, what is the right hand side? A complement intersection B complement. We can draw it here. So, suppose you take this is the right hand side, A complement is everything outside here and B complement is everything outside here. So, what is their intersection? Their intersection is again same as this part, what we drew here, which is outside both of them, outside this region. So, they are the same. Now, similarly, one can also see the other De Morgan's law, which says that A intersection B complement is same as A complement union B complement. Now, in fact, these laws also hold for infinite collection of sets, and that is the version that is written here and here. Complement of the union is the intersection of the complements, and similarly complement of the intersection is the union of the complements. Okay. Now, here is an identity that is very easy to see and it is very useful, which says that if A is a subset of B, then B complement is a subset of A complement. So, if A is a subset of B like this here and here, A is a subset of B, then B complement, that is outside B, is a subset of outside A. Outside A contains these extra elements here, this part outside. So, B complement is a subset of A complement, and this is an if and only if condition. Now, there is another notation that is frequently used. If there are two sets A and B, then A minus B denotes the difference of A and B, and it indicates the set of all elements which are there in A, but not in B, which means that if you have A and B here, then the elements which are there in A, but not in B, these are the elements, and this is A minus B. Similarly, this is B minus A, and this thing A triangle B is called the symmetric difference of A and B. It is the union of A minus B and B minus A. That means, it is both this side, this part and this part. One can say this is also that it is the difference of A union B and A intersection B. From the union, you remove this intersection part and you get that symmetric difference. Another related notation that is used is that if you have suppose B is a subset of A, then A minus B is also written as A set minus B like this. It means the set of all elements in A which are not in B. Now, we will discuss some more theory related to sets. So, one important operation between two sets is the Cartesian product of two sets. So, given two sets A and B, the Cartesian product of A and B written as A cross B is the pair, ordered pair of elements A B, where A is in A and B is in B. So, ordered pair means A comma B is considered different from B comma A. Now, for example, if you take the set A to be the set of numbers 1, 2 and 3 and set B to be the set of letters A and B, then A cross B will contain all the pairs of numbers and letters like 1 comma A 1 comma B, 2 comma A 2 comma B and 3 comma A 3 comma B, right. So, all these pairs will be there in this Cartesian product. You can think of A being two integers drawn on the this thing on the x axis 1, 2, 3 and A and B here, and then there will be these 6 elements corresponding to 6 pairs. Now, if we take the R to be the set of all real numbers, R cross R is the pairs of real numbers which are typically represented by the two dimensional plane, and every element here is a pair of real numbers, right. It is a vector with two components. So, x, y. And this definition this is often written as R2, and similarly one can also define for any set A power n, which is the Cartesian product of A n times. Now, this Cartesian product of two sets can be extended to a definition of Cartesian product for any number of finite number of sets, and what it means is that its elements are an n-tuple with components taken from the respective set, and in this particular case the sets are the same A cross A cross A cross A, but even for different sets A cross B cross C cross D etc. can be defined, where the n-tuple will have elements coming from the respective sets. Now, for example, R3 is the standard 3-dimensional space where each component is represented by 3 real numbers. It is an ordered triple of real numbers. Now, this definition can further be generalized to A infinity, where here we have taken its elements are n-tuples. So, like x1, x2 up to xn, but you can also take infinite length sequences x1, x2 dot dot dot. Then the set of such elements is denoted by A infinity, right. This is a set of all sequences of elements from A. Now, there is a further generalization of this notion as A power B, where B is also a set, it is not a number, right. So, what does it mean when you say A power B? A power B, so first of all note that if we take A2, we said it is a pair of numbers, but one can also think of this as a map of 1 comma 2, the set 1 comma 2 to A, because what does it mean if we have a map F from 1 2 to A? How do we specify such a map? It basically means we have to specify what is f of 1 and what is f of 2. So, if I give the pair of values f of 1 and f of 2, both of which are from A, right. If you specify this pair of values, then we have specified what is f, but this pair of values is also an element from A2 from our earlier definition. So, when we have a map f from 1 2 to A, that map also corresponds to an element in A2. So, if you have the set of maps from the set 1 2 to A, okay, that is isomorphic to the set A2. So, this set of such maps is denoted by A power 1 2. This is A power the set 1 2 is the set of all maps from this set to this set, and this is basically the same set as A2 itself. 2 is the number of elements in this set. So, if you take arbitrary set B, A power B denotes the set of maps from B into A, and this is basically the same set as, to be strictly speaking, it is what is called isomorphic to A power cardinality of B. If B has n elements, it is basically same as A power n, because to every map in A power B can be specified using an n tuple from A. And similarly, this quantity, the set of all sequences, can be thought of as set of all maps from the natural numbers to A, because again if you take any map of natural numbers to A, you can specify that map by specifying what is f of 1, what is f of 2, etc., right, and which is an element from A infinity from our earlier definition. It is a sequence. Now, another important structure for a given set A is the power set. The power set of a set is the set of all subsets. So, power set, the elements of the power set is a set and its elements are also sets, and they, in particular they are subsets of the given set A, and all the subsets of the set A. Now, how many subsets are there? If A is a finite set, it will also have a finite number of elements. Power set will also be a finite set. What will be the exact size or cardinality of the set? It is, so cardinality is denoted by mod A like this. Cardinality or the number of elements for finite sets is denoted by this. So, power set is also finite in that case, and its cardinality is 2 power the cardinality of A. Why is that? Because you can choose a subset of A by either taking every element, for every element you can either include it or exclude it. So, there are 2 possibilities for every set, and that means that there are total 2 power mod A number of possibilities for choosing a subset. That means there are so many subsets of A. Okay. Now, we will discuss a very important thing called relation between 2 sets. So, if we have 2 sets A and B, a relation of A into B is basically specified by a subset of A cross B, the Cartesian product. So, you take a subset of A cross B, which means that some pairs of elements in A cross B are there in R, okay, and we say that under that relation, then that pair of elements are related to each other. So, if we have, let us say, A comma B, where this is from A, this is from B, then this is related, these 2 elements are related, and we write that by either saying this A comma B is in R, or we say that A R B, which means that A is related to B, or we sometimes write R A B. So, different books follow different notations. Let us see some examples. Take the set of all natural numbers, which is denoted by this, and take the relation less than equal to. Some pairs have this relation. For example, 2 is less than equal to 3. So, less than equal to can be thought of as a subset of n cross n, that is pairs of natural numbers, some pairs of natural numbers are related by this less than equal to relation. For example, 2 comma 3, 2 is less than equal to 3, but 5 is not less than equal to 4, 3 is not less than equal to 2. So, 3 comma 2 is not there in R, okay, but 2 comma 3 is there, 2 comma 3 is there in R. Now, let us take A to be the set of all triangles. We can define a relation in A, which means of relation of A into itself, okay, called is similar to. Similarity of triangles is a relation, and that is often denoted by this tilde notation. When we say two triangles, suppose we have a triangle ABC, we say it is similar by to, let us say, PQR, two triangles. The notation is not universal, different books may use different notation. Now, some pairs of triangles are similar, if the two triangles are similar, if their angles are the same. Now, here is another relation, congruent to, congruent integers modulo some fixed number integer. So, if you take for example modulo 5, the number 5, then when do we say two numbers are congruent modulo 5? So, m and n are congruent modulo 5 if 5 divides m minus n. Okay. So, which means also that if you divide m by 5 and you divide n by 5, both will give the same remainder. Now, for example, 1 and 11 are congruent modulo 5. So, we write it this way, 1 is congruent to 11 modulo 5, 2 is not congruent to 8 modulo 5. Okay. Now, a special type of relation is an equivalence relation. A relation is called equivalence relation if it satisfies three conditions. First condition is called the reflexive property, which means that every element should be related to itself. Okay. For example, the triangles example, the similar triangles, one triangle is similar to itself. Symmetric, which means that if A is related to B, then B also should be related to A. Again, for triangles that is true, if ABC triangle is related to PQR, then PQR is also related to ABC, is also similar to ABC. But if you see, this relation is not symmetric, because 2 is less than equal to 3 does not mean that 3 is less than equal to 2 as well. Now, transitivity, this is another property which says that if A is related to B and B is related to C, then A should also be related to C. Okay. So, let us see again in this less than equal to relation, this is actually transitive, because if 2 is less than equal to 3 and 3 is less than equal to 4, then 2 is less than equal to 4 also. So, this relation is transitive. Now, if a relation satisfies all these three conditions, then we say that it is an equivalence relation. Now, one can check that is similar to, the similarity of triangles is in fact an equivalence relation. It satisfies all the three properties. Less than equal to is not an equivalence relation. Why? Because it is not symmetric, as we discussed before, right. 2 is less than equal to 3, but 3 is not less than equal to 2. Congruence modulo any integer n, right, it need not be 5, it can be any integer, is an equivalence relation. You can check every property that they are satisfied. Now, once we have an equivalence relation, one can prove that the whole set A, okay, whole set A where the equivalence relation is defined, gets partitioned into what are called equivalence classes. Now, which means it is the set, it has many subsets. So, the A gets partitioned into subsets, disjoint subsets, they have no intersection with each other. So, that every pair of elements inside one subset are related, they are all related here, they are all related here, they are all related here, here and so on. But if you take an element in two different subsets, one here and one here, then this is not related, this pair is not related. So, all relations are within the subsets. So, the whole set gets partitioned into such subsets, disjoint subsets, and these subsets are called equivalence classes. These are called equivalent, this is one and so on. So, the set gets partitioned into equivalence classes, and this can be proved easily that there are no intersections and the whole set gets partitioned. Now, let us see an example to see what kind of equivalence classes we get for this relation, the congruence modulo 5. Okay. So, if you see under this relation 0 is related to 5, 0 is congruent to 5 modulo, we are taking only natural numbers here. So, 0 is congruent to 5, modulo 5 is also congruent to 10, it is congruent to 15. So, you take any two of them, they are all divisible by 5, right. So, they give you the same remainder if you divide by 5. So, they are all related. Now, similarly, these numbers 1, 6, 11, 16, they all give remainder 1 when you divide them by 5. So, they are also related. Similarly, these give remainder 2 when divided by 5, these give remainder 3, these give remainder 4, and there are 5 possible remainders when you divide by 5. Okay. So, you get 5 different equivalence classes, and there is clearly no intersection, because one integer cannot give 2 different remainders when you divide it by 5, there is a unique remainder. So, every integer belongs to exactly one of these sets, every natural number belongs to exactly one of these sets. So, these are the equivalence classes, and one can say that this is the equivalence class of 0, or one can, because 0 belongs to this, or one can also say this is the equivalence class of 5. So, you can take any element here and put a bar here and say that this is the equivalence class of 5. We are basically taking a representative of the set where 5 or maybe 0. We usually take the smallest integer and take that as the representative, and so this we can say is the equivalence class of 0, this is the equivalence class of 1, this is the equivalence class of 2, 3, 4. So, these denote 0 bar denotes a set, it is the set of all integers whose remainder is 0 when divided by 5, right. So, that set is denoted by 0 bar, that is the equivalence class represented by 0.